In the last section, we looked at how to evaluate limits both graphically and numerically. We also looked at how we can prove a limit. In this section, what we're going to do is we're going to look at how do we go about evaluating a limit analytically. And so when we do this analytically, we have all kinds of limit rules that have been proven that we can use, right? So we are going to go through a whole slew of limit rules, properties in this video. And then in our next video, we will look at examples of how we can apply some of those rules. But let's get started and look at a bunch of these rules. So for functions that are continuous at C, and so when we say a function is continuous, we will define what that means later. But for functions that are continuous at C, the limit as x approaches c of f of x is equal to the function value at c itself, which is really nice. Basically what this is telling us is if we have a continuous function at c, when we are evaluating that limit, we can just plug in the value c into the function, and that will give us the value of that limit. Now this is built on a variety of things, and so we will look at these. So the first thing is if we were to take the limit as x approaches c of b, right, where b and c are both real numbers, then this limit is just b itself, right? So that value of b is not variable, and so as our x value gets closer and closer to c, our value of b is not changing, right? This is not dependent on x. For the next one, if we were to look at a limit as x approaches c of x itself, well, as x approaches c, then x is going to approach c, right? That makes plenty of sense. And if we have x approaching c, then x to the n power is going to approach c to the n power. So those are some of our initial basic limits. We also have a few more, or several more, I suppose. If we have a scalar multiple, right, so if we have a function that is just being multiplied by a number, right, so we have this function f of x, it's being multiplied by a number b, we want to take the limit of that function. If we happen to know that the limit of f of x as x approaches c is equal to L, then when we multiply this function by the scalar b, we can actually take that scalar and move it out in front of the limit. And the limit as x approaches c of f of x, we noticed up above, was just L. And so this will just be that scalar times the limit, L. We also have properties of limits if we have a sum or a difference of two functions. So if we have f of x and g of x, and they're either being added or subtracted, and we're taking the limit of that sum or difference. If we know the limit of f of x is L, and the limit of g of x is k, then the limit of that sum or difference is the sum or difference of the limits. Right? Basically, we are saying we can evaluate this piece and this piece separately, and then we can combine them appropriately. The same thing is true for products, right? If we have f of x times g of x, we can find the limit of f of x and find the limit of g of x. We can find those separately, and then we can take the product of those limits. If we have a quotient, one function divided by another, the same thing is true. The only time we would need to worry about that is if k was 0 itself. Right. So as long as that value of k, that limit, is not 0 on the denominator, we'll be fine. If it is 0 on the denominator, there's more work that we would have to go through. And then if we have the limit of f of x to the n power, we can take the limit of f of x and then just raise that to the n power, so it's just L to the n. So lots of properties of limits that build the foundation for being able to analytically evaluate these limits. If we have a polynomial or rational function, if p of x is a polynomial function and c is a real number, then we can just do that direct substitution. We can just plug in, replace the value of x with the value of c, the value that x is approaching. If it's a rational function, the same thing is true, provided that denominator, the bottom part, is not 0, does not head towards 0. And so here we can just plug in that value c, and things will work out fine as long as we have the appropriate provisions. Great. Some further limit theorems. So we talked about powers. The same thing is true if you have roots. Right. So the limit below is valid for all c. When n is odd, it's valid for all c when n is even. Right. So if we take the limit as x approaches c of the nth root of x, it is equal to the nth root of c. Right. So if it's an odd root, it is okay to take odd roots of negative values. That will result in a real value. We don't get real valued outputs if we take even roots of negatives. That's why we have this restriction. When we have an even root, then this is okay. We can do that direct substitution as long as it's in the domain of that nth root. Great. We also can take composite functions. So if we know the limit as x approaches c of g of x is equal to L, and the limit as x approaches L of f of x is equal to f of L, then if we have a composite function f of g of x, we can take that limit, move that limit to the inside, evaluate that to get L, and then take f of L, the function evaluated at L. So those are some of our basic limit theorems. We also have a bunch of limit theorems dealing with trig functions. So for trig functions, if we let c be a real number in the domain of the given trig function, right, so it needs to be in the domain. And so you can think back to domains for sine and cosine. The domain is all real numbers. When we have secant and tangent, the domain is all of the real numbers except for the places that would cause cosine to be 0. And so except for the odd multiples of pi over 2. That's our domain there. And for cosecant and cotangent, our domain is everything except for all of the multiples of pi, wherever sine would have been 0, and so sine is 0 at all of the multiples of pi. But what this then tells us is for those trig functions, as long as it's in the domain, right, so it's in the appropriate domain, we can do direct substitution. We can replace our x with the value of c. If it's not in the domain, then it's trickier. The limit can still exist, but we just don't know that. All right, in our next video, we are going to look at examples where we're going to use all of these limit properties, limit rules. We will see you then.